This is Lecture 8, BBSP 710. Today we're going to be discussing outliers, how you find them, what you do about them. Well, if you're not familiar with the term outlier, an outlier is an extreme value, an unusual value in a data set, and the main reason we care about them is they may represent bad data. If there's bad data in your data set and you don't get rid of it, it'll cause problems with your analysis because summary statistics like mean and standard deviation are not resistant to outliers, as I mentioned in an earlier discussion. But you can also get biased results if you throw out good data. So you want to try to identify outliers and then make prudent decisions about whether or not to remove them from your data set. Oh, just an example on how you can detect outliers in a data set. This comes from a famous experiment in the history of science known as the Michelson-Morley experiment. This data set's built into R, which is the main reason I'm using it, but just to give you some background on the experiment, it was believed that light waves were like sound waves. They have to travel through some sort of physical substance known as the luminiferous ether. And since the Earth and the Sun are moving, it was assumed they wouldn't be stationary with respect to the ether, so you should be able to observe an ether wind. And Michelson-Morley were trying to measure the speed of this ether wind. And the details of the experiment don't matter too much. Basically, they measured the speed of light coming from several different directions, hoping to show that it increased or decreased depending on the direction. And it turned out that the direction didn't matter at all. Light was going exactly the same speed in every direction, which later led to Einstein's theory of relativity. Is one of the most famous examples of a failed experiment in science. But for the purposes today, all we care about is looking for outliers in their data, because if you're going to completely change the paradigm of physics, you would want to make sure that it's not the result of bad data. So at any rate, a common rule of thumb for detecting outliers in the data is that anything that's more than 1.5 IQRs above the third quartile or below the first quartile is a possible outlier. Interquartile range, as you'll recall, is the difference between the third and first quartile. This is only a rule of thumb. Don't take it as gospel. You'll end up deleting good data if you mindlessly apply this rule without thinking about whether or not if you mindlessly apply this rule without checking to see if the data is actually valid. So just a simple example of how you might do this. Say you had the data set with these 5 observations, 50, 70, 83, 92, 100. In this case, the first quartile is 70, the median's 83, the third quartile is 92, and the interquartile range is 22. In this case, so to find the lower limit for your outlier detection, 1.5 times 22 is 33. You add 33 to the third quartile, get 125. You subtract 33 from the first quartile, you get 37. There's no data points outside that range, so no putative outliers. And if you want to do this calculation in R, you can use the sort and quantile commands. I create this data set called test, which has the same data that I outlined on the previous slide. I sort it, I compute the quantiles, then I compute 1.5 times the interquartile range and add it to the third quantile and the first quantile. We see that no data points are outside that range. I'll conclude there's no outliers in the data set. Now we'll go to the Michelson-Morley data. This data set, as I said, is built into R. The name of the data set is Morley. So if I were going to apply that procedure to the Michelson-Morley data, I would sort it from smallest to largest and then calculate the quantiles. 25% quantile is 87.5. The 75% quantile is 892.5. So I add 1.5 times the interquartile range to 892.5. I subtract 1.5 times the interquartile range from 807.5. I get 680 and 1020. So the putative outliers in this data set I marked in red are 620, 650, and 1070. In practice, you usually won't want to do this. An easier way is to just plot a box plot. As I discussed in the previous lecture, and the whiskers in the box plot go to the most extreme observation that are the most extreme observations that are within 1.5 times the IQR of the third and first quantile. So we see the one dot at the top, the two dots at the bottom, both corresponding to the data points that I marked in red on the previous slide. And sometimes you'll use other criteria for detecting outliers as well. Some people are suspicious of observations that are more than 3 standard deviations from the mean. The IQR-based criteria is probably better since IQR is robust against outliers, whereas standard deviation not. But as I said, you also don't want, this shouldn't replace common sense, that you want to look for out-of-range values and things like that. For example, if the data is height, and if you have a data set of heights of adult humans, and one height is listed as 1 foot 2 inches, you should be suspicious of that. If a height is listed as minus 3 feet, you should be even more suspicious of that. Sometimes bad data points like that won't necessarily show up on a box plot. You just have to look at the range of your data and use common sense and say it doesn't make sense for a number to be that low. The next question is, so should outliers be removed? If you keep bad data in your data set, you can get incorrect results, particularly for things like means and standard deviations. But if you remove good data, then you can end up with biased results. And in general, this is a judgment call, and deciding when you should remove data is as much an art as a science. But there's some general guidelines that you can follow. For example, if an outlier is out of range or physically impossible, if someone has a negative height, for instance, you should definitely remove it then. If you can verify that your experiment malfunctioned or that the experimenter made a mistake, then you would definitely want to remove it then. You may have to check your equipment, your charts, whatever the case may be. And if there's a big gap between your outlier and the rest of the data, it's more likely to be spurious. If the data, for example, is extremely right skewed and you see a couple dots past the end of the box plot, that's not terribly unusual. On the other hand, if almost all the data is clumped together at the center and you just see a few at the very extreme end, then it's more likely that those are spurious. And if there's a couple weird values in the same batch of the data is more likely to be bad as well. But like I say, none of these are conclusive proof. You just have to use good judgment and common sense. For the Michelson-Morley experiment, we don't have their original notebooks or recording equipment or whatever the case may be. But the data set in R did show that it consists of 5 different batches, so let's do separate box plots in each batch. And we look at it in experiment 1, or we look at the box plots by batch of the Michelson-Morley data, and we can see batch 1 tended to be a little higher than the other 5 batches. In particular, the most extreme observation that was marked as a possible outlier was in batch 1, and it does not show up as an outlier when you look at those batches separately. And it is interesting to note, though, that the lowest observation, or I guess that's the second lowest observation, was also in batch 1, which is a little bit weird given that batch 1 tended to be higher, but batch 1 also had higher variance than the other categories. And the 620, the data point with 620 seems to be really low for batch 3, which was otherwise tightly compact together. I mean, even the observation of over 700 shows up on the box plot just because all the others were so tightly packed together, but it's hard to know for sure. So, tentative conclusions, it seems like 620 is the least likely to be real, but based on these plots, I probably wouldn't throw out any of the data points unless I could go back and look at their original equipment and verify that something malfunctioned. None of the observations are completely implausible or out of range. If you're curious about the R commands that were used to generate these box plots, they're here. Like I said, the first is for the full data set, the second is by batch. This is similar to the commands for plotting data that I described in the previous lecture, but it's, if you want an example, there you go. Second example of outlier detection and removal comes from an actual data set that I worked on a few years back that one of my collaborators in the medical school here was trying to develop a clinical assessment for pelvic pain. She palpates the patient in several different locations and measures how much pressure the patient can tolerate, and the objective was to predict the patient's tolerance to pain based on the site of the examination and whether or not the patient has a chronic pain condition. So we built this model to predict the tolerance based on site and the pain condition, and most of the time patients with the same disease status had really similar tolerances at any given site, but there were some major outliers. So the question was, were these outliers real? So here's a box plot of the errors in our model, the difference between the expected tolerance and the actual tolerance, and you can see most of the errors were very close to zero, almost exactly what we predicted, but the distribution has ridiculously heavy tails with some really large errors for some patients. Here's a histogram. Once again, I mean, the number of people with the larger errors is so small you can't even really see them on the histogram, but they're there, which is why the histogram goes out to 15 rather than just being clumped around 0. So that raised the question, do these outliers represent bad data? In the perfect world, we would want to plot the error for each patient separately to see if some patients had higher errors than others, but we had over 100 patients in this study, so that would have been hard to visualize. So what we did is we plotted the error against the predicted tolerance, the idea being that similar data points should have similar predicted tolerance. Oh, if we see one particular predicted tolerance that has really high error associated with it, that probably indicates that all the bad data is coming from the same patient. We did that, and it seems to be that in one case there was an unusually high predicted tolerance and really large errors associated with that, so that looks like our hypothesis was correct, that it was in one particular patient or a small group of patients that were producing all the questionable data points. I think I just said most of this. Indeed, as we looked at it more closely, it looks like almost all the extreme values came from 4 particular patients, so we pulled the charts for those particular 4 patients for closer examination. And for one of the patients, the measured tolerances were physically impossible. My collaborator simply wasn't strong enough to exert that much force. We concluded that's clearly wrong. We'll eliminate that patient. For a second patient, we checked the logs and it showed the equipment malfunction that day. That patient got tossed as well. The other two patients, we couldn't find anything wrong, and they had smaller errors relative to the first two, so we kept them in the data set. Like I say, it's a judgment call. You just have to look very carefully, decide whether you believe the results or not, and do the best you can. And just to give you an example of where things can go wrong if you just mindlessly apply this 1.5 times the IQR rule without using common sense. An example of this is stock prices. This data set consists of the closing price of France's CAC stock market index every day between 1991 and 1998, and there's a total of 1,860 observations. Oh, if you just mindlessly plot the box plot, you say, whoa, there's 10 billion outliers there. We must have a lot of bad data in this data set. But, is that actually the case? If you look at the data more carefully, it's due to the distribution of the data, not bad data. This is a plot of the closing value of the CAC over time, and you see throughout most of the decade of the 1990s it hovered around 2000 or so. At the very end of the decade, suddenly it jumped really high. And as you'll recall, in the late 1990s there was a major stock market bubble going on, so you ended up with not much movement through most of the decade, but then sky-high stock prices for the last year or two. So there was nothing wrong with the data. It was just the result of suddenly the data changing pretty drastically. And the point here being that unusually large data points are not necessarily bad data that you should mindlessly remove. And if you're curious about the commands that I use to create this, there's the command to create the box plot. I also use the plot command to create the plot of the stock market data over time. I'm not going to cover that in this course, so don't worry too much about the details. And we will use the plot command later, but not for this type of plot. And as I said, couple other R notes when I say EU stock markets bracket, comma 3 bracket, that tells R to reference the third column of the EU stock markets matrix. I could have just said EU stock markets $CAC. That square brackets to extract a certain column works just as well. The plot command is very general. You use it to choose a plot appropriate for whatever data set that you're working on. In this case, it recognizes EU stock market as a time series and creates a time series plot. We're not going to cover time series in this course, so that's just an FYI. And another example of when you can get in trouble if you apply these rules mindlessly without good judgment, there's a data set in R that records the number of sunspots observed every month between 1749 and 1997. We have a total of slightly under 3,000 observations, and we want to check for outliers in this data set. So if you just mindlessly apply the 1.5 times IQR rule, you see data with a really heavy right tail, and you think, well, are all those outliers? You wouldn't want to just mindlessly delete that data, though. One way to see if the data looks legit or not is just to look at a histogram, which I'll show you on the next slide. And you see most months there's relatively few sunspots, but the distribution has a very heavy right tail, and the number of sunspots per month seems to decrease linearly as you go to the right. So the fact that we see a few months with very high number of sunspots doesn't seem particularly implausible. One would be concerned if almost all the data were clumped around zero, then we had a few out in the hundreds. Here it kind of gradually goes out to the right, so you would probably conclude that there's nothing inherently problematic about this data. And yeah, basically the data just has a really heavy right tail. We usually don't see large numbers of sunspots in a month, but it does happen, so the outliers are probably real data. And once again, here's the R commands that I use to do this, box plot and histogram. It's really similar to the commands I showed in the previous lecture. Things to remember for today is that outliers are extreme values in a data set that might be spurious. You can detect them by drawing box plots or looking at the IQR of the data, but these methods are not foolproof and shouldn't be a substitute for common sense. When you find an outlier, you should try to figure out if it's real and then remove it if it isn't. This is often a judgment call, but you can have some idea using the guidelines that I described in the lecture today.